Hi friends, let's have a look at problem 1038, binary search tree to Greater Sum Tree. This is a tree-related problem, which is also a daily challenge problem. So in this video, we are going to analyze this problem. So here we are given the root of a binary search tree, abbreviated as BST. So we want to convert it to a grid tree such that each key of the original binary search tree is changed to the original key plus the sum of all keys greater than the original key in the binary search tree. So here is the definition of the a binary search tree. So here we have two examples. The first example is the second example is sort of trivial, right? So let's focus on the first example. So here is the representation of the tree, right? So notice that for the root, originally it's 4, right? All the values larger than this value is in the red. So in other words, we have 5, 6, 7, 8, right? So 5 plus 6 is 11. So 7 plus 8 is 15. So the total sum of these four numbers is 26. Then 26 plus 4, you get 30, right? So similarly for 6, right? For 6, the larger ones will be 7 and 8. So you get 6 plus 7 plus 8, that will be 21, right? So, but if you look at 1, so then all the larger ones will be the root and then the red subtree, right? So you can, similarly, you can get 36, right? So also notice that for this 36, we need to also add 2 and 3, right? So because up to this one we get 30, and then plus 1 is 31, then plus this 2 and 3, you get 35. So similarly here you have 0, right? And then up to 1 you get 36. So here you add this 0, you get also get 36. So from this analysis, you can actually have the impression that this problem can be have some very elegant solution. So here, first let's look at the constraint before we move forward. So here, the number of nodes in the tree is in this range. So at most 100 nodes. So this is actually a small size problem, and the node values are in this range. So because we have at most this number of values, and we have this range, and also the values in the tree are unique. So this assumption, all the values in the tree are unique, actually simplifies the problem, right? So here, for solving this problem, we are going to take a method which is sort of verbose, but our purpose is to understand the problem logic. So what we are going to do is to use a binary search tree property. So the binary search tree property is that for each node, for given a root, so the right subtree contains values greater than the root value, and the left subtree contains values less than this root value. So this relation holds recursively. So here we want to make a first observation, that is, if we do in-order traversal, right? So in-order traversal, then the resulted array will be a strictly increasing array due to the BST property, right? So then for each node value, the new value will be the suffix sum from the node value index to the very end of the array, right? So let's have a look at this example 1. So for example 1, if you do a traversal, in-order traversal, so you can do left subtree and then 4, then right subtree. So similarly for this one, you do left subtree, so the array will be, say, 0, right, left subtree, then 1. Then you do 2, 3, then you do 4, right? And then you do 5, and you do 6. Because for the tree rooted at 6, you first do left subtree, you get 5, then you do 6. Then similarly for the tree rooted at 7, you do left subtree, but it's null. Then you do 7, and then you do 8, right? Then for this 0, the value 36 actually is all those values to the right in this one, and for this 1, it's actually all the values starting from 1 to 8, and for 2, the larger values will be this 1 and 4, 5, 6, 7, 8, right? So to the right. Then if you compute the partial sum for the suffix, so suffix sum. So what we get, actually, let me copy this part. And then we do 7 plus 8 will be 15, right? 6 plus 15 will be 21. 5 plus 21 will be 26. And this will be 30. This will be 33. This will be 35. This will be 36. And then this will be 36. So because the values are unique, so we can see 0 will correspond to 36, and 1 will correspond to 36, and 2, 35, 3, 33, and 4, 30, 5, 26, 6, 21, and 7, 15, and 8 corresponding to 8, right? So this example also tells us how to do the coding. Let's look at one way of doing this coding. So here actually we can do one pass, but for the purpose of explaining, so we are going to first write a traverse function. So here given root. So here I'm going to do another traversal. We can write this another traversal using the recursion, right? This is very simple. So we're going to return traverse root left, and plus the root value plus traverse root right. So this we are using the binary search property, but the base case for this recursion is if root, right? Otherwise, so we just return an empty list. So we can understand that because in this problem, the number root node is at least 1, but we are writing recursion, we need some stop condition. So if the tree, if we arrive at a leaf and then we continue, so we're going to get the empty one. That's why we have this one. You can also understand this else as the base condition for this recursion. So you can print out this, right? So let's print out the list for example 1. So you get 0, 1 to up to 8 as here, right? So now with that done, we can let's name this one as the values. Then we want to compute the suffix sum from this list. So this is actually very easy. So we can see cumulative values. So we can make a copy of this one, and then we do iteration in the reverse direction. So basically for say I in range, say length of current values. So this is the last index, but the last index will remain the same. So we can start from -2. So we end, the decrement will be -1, right? So this is the ending index, but not included, right? Then decrement by 1. So we ending at the index 0. So for this one, then cumulative values, the current one, so is incremented by cumulative values at next index. Because we are starting from here, we are always in range. So in other words, I plus 1 is always in range. So this way, we are going to get this suffix. Let me print out this. Current values. You can see you get 36, 36, this 15, 8 as this one, right? So now we want to do modifications. So in order to do modifications, so we can do a traversal of the tree, and then we can use the assumption that all the values in the tree are unique. So for convenience, we can first make a dictionary so that we just see we can see the key is the original value and the value will be the new value, right? For key value in, so we can use zip function, the values, the accumulated values, right? So this is just for convenience. You don't need to do this in principle. So then we can do a traversal. So we can do another traversal. So you can do whatever traversal you want. So here we can use the assumption that the tree is not null. So we can use a depth first based traversal. So this is actually very basic, right? So we have this. So we can do s pop. Then for the current node, let's look at the value. So we just need to reset the value to be d node value. We map the current value to its cumulative value, right? And then we check if node right, and then we are going to do s append node right. If node left, so we're going to do node left, and then we're going to return the root itself. So before we do the test, let me comment on this. So this order is not, it does not matter. But if we write like this, actually you can use one simple example to test this corresponding to a specific order. So let's see, you have 0, you have 1, you have 2, right? Then the stack is initially 0, right? So you pop to 0, you pop to 0, and then you check the right one. So you put 2 here, and then you put 1 here. Then you do pop, right? You are going to get 1 and a 2. So this is actually a pre-order traversal, right? So, but you know, for this problem, you don't need to pay attention to this order. But if you want to write pre-order traversal, you need to first check the right subtree, right? So now let's do a test. It passes one example. Now let's do the generic check. Yeah, it passes all the cases. So this is the one way to solve this problem. But as we mentioned here, when we walk through this example, once you computed the value for 4, right? Then when you compute 1, you just need to add the 1 in the right subtree of this 1, right? Plus the value at 4, right? So this way actually save a lot of operations. So this means that this code can be greatly improved. But for now, we are going to content ourselves to the current format. So this is basically about it for the current problem. So you can look at these notes. So this question is the same as problem 538. But if you look at this problem, so you can see that in this problem 538, this code, if you copy to this problem, it will not pass because of a special case. Because in problem 538, the tree can be null, but you just need to do a check, right? You just need to add if not root, it just a return, right? So this, if you write like this way, this will pass the current one for sure, because we don't have this situation. And then you copy this code, it will pass this 538 due to assumption. This is due to the assumption difference in problem 538. But for this problem, you just need to comment out this one, right? So with that said, I guess that's it for the current problem. Thank you.